So our second speaker is Professor Yousung Jung, from South Korea. So Professor Jung received a PhD in theoretical chemistry from University of California, Berkeley, with under the supervision of Martin R. Gordon. And this was followed by a postdoctoral position at Caltech with Rudy Marcus. And after that, he went back to South Korea, where he became a faculty member at KAIST in 2019, and now he's a full professor in theoretical chemistry. And he leads a group that develops electronic structural methods, statistical modeling, and machine learning approaches to develop efficient catalysts. So he's been awarded, he received several awards, including the Paul Medal in 2018, the Korean Chemical Society Young Physical Chemist in 2017, and the Distinguished Lectureship Award from Japan in 2015. So I've read a very interesting paper published by his group in 2018 on chemical science, on active learning with non-ab initio input features for the efficient CO2 reduction catalyst, and I'm looking forward to hear your recent work. Thanks a lot, Yousung, for your talk.
Okay, thank you very much, Davis, for the kind invitation on the introduction. It's a great pleasure for me to speak in this Thomas Young Centre seminar series. So I gather that this seminar series has a theme of CO2 utilization and some aspects of that, but my talk actually is going to be about a little bit more general, and I'll be more focusing on the methodologies, data-driven approaches to address material science applications. And so I will talk about the piece of work that Davis just mentioned, active learning of approach for developing a model for binding energy predictions, but I will also talk about other aspects of machine learning for material science in general. So I hope that that's okay. Okay, so to set the stage, the ultimate goal of material science is really to discover novel materials with desired properties, and those materials could be molecules like antibiotic molecules shown here, or they could also be some crystal structures for battery applications. And in achieving this goal, the idea of materials informatics is really to use data to understand the structure property relationships of materials. And by learning that structure property relationships, we want to predict the properties of the materials given the structure, or you can go the other way around. In other words, you can define the property that you want to achieve first, and then come up with a structure that would have such a property, and that would be the inverse design aspect. And so the idea of materials informatics is really to dramatically reduce the time and cost for the novel discovery using these data-driven approaches. And there are several key ingredients to do the materials informatics. Because it's data-driven approach, the most important part is, of course, the data. And you also need to represent the data in a machine-readable format. And once you have the data and representations, then you can make predictions, and that would be the property predictions. Let me close this window. Hold on. Well, I don't know how to close this window. Anyway, so once you have this tool to evaluate the properties for the given structure, then the next challenging task is to explore the chemical space. Exploring chemical space is especially difficult because chemical space is literally almost infinite, and so finding a material with a target property is similar to finding a needle in a haystack. So you need to have a very efficient algorithm to explore the chemical space to achieve that goal. So today I'm going to talk about these aspects, property predictions using machine learning, and also exploring chemical space using these algorithms to do the inverse design. So for the property predictions, like I said, once you have the data and a way of representing the data, then you can perform simple regressions to make predictions, and sometimes sophisticated predictions. And so far, the majority of this machine learning work in material science has been based upon feature engineering. In other words, you use simple attributes of the materials to compute the properties that are harder to compute or that are harder to experimentally measure. And for example, for catalysis applications, a lot of what we do is basically binding energy calculations for key reaction intermediates, because those energetics determine often the activity of the catalyst. And so, so here is an example of predicting the CO binding energies using electronegativities, d-band centers, d-band width, and other moments of the densities. And they show the accuracy of 0.1 electron volt. That's the work by Singh and co-workers. And we wanted to also have a model, and some of these actually features need to be calculated using density functional calculations. So we wanted to have a model for us with which you can compute without any ab initio calculations. So to that end, we propose to use two mean field descriptors, electronegativity and the d-band width. And for computing the d-band width, you can use density functional calculations, but you can also take a simple, like a mean field model, and namely linear Murphy-Din orbital model. And there's an analytical expression for that model to compute the d-band width. And so based upon these two simple mean field descriptors, we were able to obtain the accuracy of 0.16 electron volt of error. This is not a spectacularly accurate result, but this is a reasonable in the sense that we only use two simple mean field descriptors. And to improve these models even further, people are using different representations, namely structural encoding. Basically here, you basically use the structure of the molecules, the structure of the materials to that go into the model. This is similar to a situation that where we use the structures or the Hamiltonian of the molecules in electronic structure calculations. There are different ways of representing the structures of the compounds, but one that's quite promising is the graph representation of the compounds. In a graph representation, one basically represents the atoms as nodes and bonds as edges. And what's important is the ability to incorporate the chemical structures. In other words, the atom A should know that atoms B, C, and D are nearby, if you look at the left-hand side. And atom B should know that atoms A, E, F, and G are nearby. And those sort of environmental aspects can be incorporated into the algorithm by a mathematical operation called convolutions. So by performing a couple of or several convolutions, you can actually encode entire molecular structures. And you can do the similar thing for crystal version. And it has been indeed shown that this graph neural network yields pretty promising results for energetic properties and also mechanical properties. And this graph-based neural network is sometimes called in literature as a message passing neural network, because the way that convolution sort of encodes a structure is similar to the message is transferred from one atom to a nearby atoms and so on. So this MPNN, or message passing neural network, is essentially the same as graph neural network. So for catalysis applications, this graph neural network has been used by the Ulysses group a couple of years ago, and they used a variation of this graph neural network to compute the CO binding energies. And they were able to obtain about 0.13 electron volt or better for the binding energies of CO and H for about 12,000 cases for for different kinds of alloys and metal catalysts. But one downside of this approach is that we needed to have optimized structures before we apply this model. But we know that once you sort of optimize the structures, then you already have the binding energies. So for us, the motivation was to have a model that would not require geometry optimizations. They would not require these relaxed structures. So we proposed to use a pseudoatom site labeling method. So for example, if you look at the top size, then hydrogen atoms are bound on top of the top site, bridge site, hollow sites. And in general, you need to optimize these structures, and those optimized structures go into the model. But in our case, you remove those atoms, like hydrogen atoms, and instead we sort of color the metal atoms that these hydrogen atoms are bound, and we call them pseudoatom site labeling, and then use this simple slab with different site labeling for graph neural network. And that allows us to bypass the geometry optimization for the isorbate bound geometries. And then if we actually use the bulk structure from Materials Project database, then you can actually go even further, because those structures in the MP database are already optimized. And so all you need to do is take that bulk structure, unicell, and then cut that bulk unicell along a particular facet, and then apply this pseudoatom labeling for the slab. And that allows us to completely remove the DFT optimizations. And here is the benchmark results. And so our prediction accuracy for CO and H are pretty comparable to the previous work by Ulysses and Grossman groups. And the key difference, however, is that our approach does not require geometry relaxation for the surface slab or the isorbate bound structures. And so we thought that this could be a practical deep learning representation for catalyst screening applications. And in fact, the motivation actually of us working on this pseudoatom labeling method, which does not require this isorbate bound geometry relaxation, was to study this system. This is the jagged platinum nanowire synthesized by the Young group, and Young group actually reported in Science and Nature Catalysis about the performance of this material for oxygen reduction reactions and hydrogen evolution reactions. And so we wanted to understand, and that they reported that this jagged platinum nanowire has a very high activity for those two electrochemical reactions. And this jagged nanowire, by the way, is synthesized from nickel platinum straight nanowire, and they de-alloy the nickel. And the remaining platinum has very sort of a up and down rough geometries, and that's why they call it jagged platinum nanowires. And so we want to understand why this jagged platinum nanowire has such a high activity for HER, for example. And it is well known that even for platinum, depending on different facets, they have different coordination environments, and they have very different activities. And if you look at this jagged platinum nanowire, then the coordination environments of platinums are all over the places, right? So because it's basically amorphous. So conventional density functional calculations would not work to study this system. So that's why we actually worked on this pseudoatom site labeling method, which does not require geometry relaxations. So we developed a end-to-end simulation workflow combining reactive force field calculations, DFT, and machine learning. And this is where the pseudoatom site labeling method comes in. And this is indeed the key aspect of the entire workflow. And then we use these kinetic Monte Carlo simulations to obtain experimental measurements, namely the current densities as a function of the potential. And then based on those simulations, we understand the mechanistic insights. And on the right-hand side, you see these experimental current densities obtained from the Young group, by the Young group. And solid line is the experimental curve, and open circles are the simulation results, and they have reasonable agreements. And we also get reasonable agreements for various properties, parameters that are obtained from this taper plot. And so with experiments well reproduced using these multi-scale end-to-end simulation workflows, so here is the interesting mechanistic insight that we obtained for this system. For those of you who are not too familiar with the hydrogen evolution reactions, there are mainly, if you look at the bottom left corner, the two sort of hydrogen evolution reaction consists of two different reaction steps. One, hydrogen adsorption from water. So the surface picks up the proton from the water. So that's the Balmer step in green. And the next step is the coupling of those two adsorbed hydrogens to produce hydrogen molecules. And that's taper step. And we find from these multi-scale simulations that, so if you look at these jagged platinum nanowires, then some sites are very good at picking up protons from water, but those sites may be bad at coupling the reactions. But some other sites could be very good at coupling those reactions, or even though they are bad at picking up the protons. So we realize that there are some sites that are Balmer favorable, and there are some sites that are taper favorable. And because the diffusion of these adsorbed hydrogens from one site to another is very fast in platinum case, so protons can be picked up in the Balmer favorable site and then diffused to the taper site, and they get coupled to produce hydrogen molecules. And so this is a well-known bifunctional mechanism that we found. But what's very interesting was that in conventional bifunctional mechanism, you need two materials, one material doing one thing good, and another material doing another thing well. And but in our case, it's a monometallic system, and only the morphology allows us to have this bifunctional mechanism. And that bifunctional mechanism gives us over a 400% enhancement in kinetics compared to Balmer sites alone or taper sites alone. Okay, so far I've talked about this property predictions using feature engineering or graph representations, but these models actually, if you give an input to the model, then those models spit out one number. But we know that these models have uncertainties, and in this publication, which I'm not going to talk in much greater detail, we've shown that if you consider those uncertainties when you in your screening, then you can actually increase the discoverability of the materials by more than a factor of 2. Okay, so far I've talked about these property prediction aspects, so basically the forward prediction. And in the next 10 minutes or so, I'll be talking about this inverse mapping and a way of exploring the chemical space efficiently. In this review article, we sort of categorized machine-enabled inverse design strategies into 3 different categories, namely high-throughput virtual screening, global optimization, and generative models. So due to the time limit, I'm going to focus today on the generative models. So what is a generative model? Generative models are mainly used in image processing in IT industry. And for example, you can show a lot of celebrity pictures to the machine and train the machine. And then after training, the machine will be able to produce fake celebrity pictures. And that's what this generative model does. And as you can see, these are not the actual celebrity pictures. These are AI created celebrity pictures, fake pictures. And similarly for a portrait, you can do that. And so as a chemist, we wanted to use these generative models for chemical science. And this is a sort of one example of a generative model, namely autoencoder. So in autoencoder, you have two networks, encoder network and decoder network. And what encoder network does is you basically represent the molecule in some machine readable format, such as smiles. And the encoder compresses the data and maps that molecule into a smaller dimensional space, namely latent space. And then what decoder does is decoder takes this latent vector and recovers back the original molecule. And so as a whole, this autoencoder doesn't do anything. It basically compresses the data and then recovers back. But what we are left with is this latent space. So if you look at this latent space in the middle, then first of all, it's continuous, unlike molecular in material space, which is discrete. And second of all, if you sort of associate each latent vector to a corresponding property, then you can sort of construct some kind of contour map as shown here. And just by looking at this contour map, you can immediately see that this red region would be the region where the properties of the materials would be optimal. So all you have to do then is sample around this red dot region and then decode those structures. And any structures that come out of those decoding are sort of new materials with the desired property we expect. And so this is the first work that this autoencoder was applied to solid state crystal structures that we did back in a couple of years ago with Alan Asperguzik. And so here we represent the solid state materials in image representations, and then you construct this latent space. So every point in this latent space corresponds to material. So in this case, we used we applied the method to vanadium oxide chemical space, and so you can sort of see that this latent space is sort of structured, and you can see a stable sort of vanadium oxide region and unstable vanadium oxide regions, and by sampling around the stable regions, you might be able to find the new vanadium oxide structures. And so indeed, we interpolated between the two known vanadium oxide compounds. So these red open circles are the interpolations that we made between the two known vanadium oxide compounds. Remember that so this interpolation cannot be done in discrete, like a real material space, but you can do this kind of interpolation in this latent space because it's simply sort of a real space which is continuous. If you look at the left-hand side corner, then that's a formation energy as a function of vanadium atomic fraction, and the blue circles the vanadium oxide compounds in the materials project database, known compounds, and the orange circles are the ones that we generated using our generative models. And you can see that those V508, V304, and so on, they are completely new compositions that are not in the database, which we generated using our model. And many of them actually have low formation energies, meaning that, or suggesting that they might be synthesizable. And if you look at the actual structures shown on the right bottom, then they are perfectly normal looking. And some of them has even space group symmetry. Now, so this is the autoencoder generative model we applied for material science. And there's other kinds of generative models. And this is generative adversarial network. In short, it's called GAN model. And the GAN model is known to produce more realistic images. And so we developed this GAN model for material science, and we applied that to magnesium manganese oxygen ternary compound space. So on the left-hand side, so it's a phase diagram of magnesium manganese oxygen, and the open white circles are the convexal minimum, true minimum structure, and the red circles are sort of metastable known structures in the database. On the right-hand side, we have the same phase diagram of MgMNO, but you can see that in this, now these are filled with structures that are generated using our GAN model. And you can see that GAN model can actually fill up the gap between the known structures. So in other words, you can actually explore the hidden portion of the chemical space by utilizing these generative models. And because these MgMNO systems, compounds, are known to be active, so for some cases, for the anode applications, we actually have gone through all of these newly generated MgMNO compounds to see if any of them might be sort of promising for the anode applications in terms of band gaps and probe stability. And these stars are the MgMNO compounds that are in the literature, either experimentally or computationally, as promising photoanode applications. And open red circles are the ones that we generate using our models. And you can see that many of them are within the promising region, like which is indicated as a dotted blue box here. And so these are the candidates that might be experimentally testable. Okay, so now as a computational chemist, we know that many of the compounds or materials that we design end up not being synthesized due to the synthesizability issue. And so predicting the synthesizability of the materials could be actually is essentially one of the last puzzles that needs to be solved. And synthesizability prediction is very important, but very difficult because it involves thermodynamics, kinetics, reaction conditions, precursors, and so on. And so it's difficult to predict. And from the computation or machine learning point of view, this is also difficult because we only have the positive data. In other words, if a material is synthesized, then we know that it's synthesizable. But if a material or hypothetical material obtained by substitution, if hypothetical material has not been synthesized yet, then that doesn't mean that it is not synthesizable. It may mean that we haven't been able to synthesize it, but it still could be synthesizable. In other words, this synthesizability prediction only has the positive data and no negative data. So one cannot use conventional sort of classification machine learning method. So here we used a positive unlabeled machine learning method, which is iteratively performed. So I'm not going to go into the details, but if you have questions, then I could answer the questions. So we used 50,000 positive data from materials projects. So these are the data materials with the ICSD ID, and there are about 80,000 unlabeled data that are obtained by substitutions of the synthesized materials. And our model after training shows about 87% of accuracy. And as a validation, what we did was we trained the model using the synthesized data up until 2015, and then tested if our model can predict the synthesizability of the synthesized materials between 2015 and 2020. And again, consistently, our model predicts about 87% of the time correct. And what's interesting, we found was that what was shown on the bottom left corner, because synthesizability is a very complicated phenomenon to predict, the most widely used method or way of estimating synthesizability, including us, is usually based on formation energies or decomposition energies. But we find that x-axis, which is the synthesizability score, and the y-axis is the energy of a hole, they do not have strong correlations. So that strongly indicates that synthesizability is much more than simple thermodynamics. And on the right bottom, we've tabulated the synthesizable materials in various databases. And for example, MP Virtual and OQMD Virtual, they have about 10 to 20% of materials in those databases are considered synthesizable based on our models. And IMAGEN is a generative model that I showed you 10 minutes ago, and that has about 4% synthesizable materials. If you look at like 100, but if you generate 100 materials using IMAGEN, then only 4 of them might be synthesizable, and that's pretty low, but that's understandable because these generative models actually generate completely new structures using the distributions that the model has. So this is my last slide. So as a further validation of synthesizability prediction model, out of 80,000 unlabeled hypothetical materials, we ranked according to synthesizability score, and then looked at top 100 candidates and looked up the literature if any of them had been indeed synthesized. And we find that actually 71 of these 100 hypothetical materials have indeed been synthesized. And although they have not been deposited in the repository, but they have indeed been experimentally reported with powder diffraction patterns, for example. So our model is actually yielding very sensible results based on these benchmark results. All right, so today I talked about use of machine learning to study materials and chemical science, focusing on property predictions and exploring chemical space using generative models. And of course, there are many challenges, opportunities ahead. For example, the synthesizability prediction that I talked about today is just the beginning of what needs to be explored. For example, our model uses the structure of the crystal structures as an input, or hypothetical structures. But compositions would be more useful for experimentalists, or incorporating experimental conditions, or thermodynamics could also improve the model. So I'm sure there are many exciting opportunities that lie ahead. All right, so that's the end of my talk, and all of the work that I presented today were done by 4 brilliant students of mine, Juhan, Kunho, Jidon, and so on. And I would also like to thank my collaborators, Alan, John, Bill, Tao, Xiangfeng, and Zach. And I would like to thank you for your attention as well. So thank you.
Thank you, Yousung, for your very nice talks. So I would like to ask to the audience if they have any questions for him. And while I wait, I just want to ask you questions related to the beginning of your talk, where you mentioned that you use kind of the binding energy, for example, for CO2 or CO as the indicator for the activation. I was reading a few recently some papers where they indicated maybe for CO2, the binding energy could not be maybe a very good indicator, but maybe you should rely on CO2 binding, or maybe even better, carbon, the elongation of the carbon-oxygen bond. Could your model be, readapted to take that into account, if that is the case?
Right. So CO binding itself is easier to predict. For example, if you should look at, for example, COOH, then it's larger than CO, and so there are multiple binding sites, so they could bind to like 2 different metal sites, for example. Those are harder to predict, but for CO, which would only have one metal atom or bridge site or hollow site, they are easier to predict. And so I would say CO binding energy prediction is more straightforward to make a model, but so larger intermediates would be harder to make a model for. And but once you have enough data, then I'm pretty sure that one should be able to come up with the reasonable model. But I had a big assumption that once you have enough data, because you need to have enough surfaces in your training set so that the model knows enough about the chemical space that it needs to explore, right? So once you have enough sort of catalyst surfaces, alloys and oxides, then I think that one should be able to come up with a model with a reasonable accuracy.
So there is a question here from Mikhail Stamatakis from UCL is asking if I was wondering for the work on nanowires, is it possible that leftover nickel atoms at high dilution in the final material could carry out some of the chemistry as well?
I missed one part. Leftover. I'm sorry, but leftover.
Can you see the chat, Yousung? Can you?
Yeah. Let me. Okay. Let me then stop the sharing and then look at the chatting. Okay. So I was wondering for the work then whether it's possible the leftover nickel atoms. Oh, I see. Yeah. This is very important question. So the Nature Catalysis paper by the Young group published in 2019. These leftover nickels, actually not leftover nickels, they actually find that nickels atoms are almost as a single atoms, like dispersed. So they actually act as a very important active sites, right? But our case, as far as we can tell from experimentalists, that nickel, there are no nickel atoms, and so we assumed, based on experimental characterizations, that the jagged platinum nanowire consists of only platinums. So that sort of possibility of leftover nickels was excluded based on experimental characterizations from our experimental partners. But Michaela, you're right that in certain cases, actually you can actually utilize and the fact that nickel can be an active site, and that's the work of 2019 Nature Catalysis paper.
Great, thank you very much.
Thank you. Yeah. Thanks a lot, Yousung. So, are there other questions for Yousung? Otherwise, I think we should, thanks a lot our speakers, especially because I think it's probably 1:30 in South Korea. So yeah. I think we should thank them twice, given the time that they were available to deliver their talk. So thanks again, and I hope to see you in face-to-face soon. Okay. Yeah.
Thank you.
Thanks a lot. Have a nice evening, or well, good night in your case. Yeah, bye-bye.
Bye. Bye. Thanks.
Bye.
Yeah, okay, bye.